Swayam Prabha. Digital India. Educated India.
Okay, so somehow when you have this bipartition, you the graph, the G prime, becomes disconnected, and if it's if it's not bipartite, then this G prime will be connected. Okay, so now in my streaming world, can I use this claim to check for bipartition whether a graph is bipartite? Right. So I have this current graph, edges are coming, and I need to check whether this new graph is bipartite. Okay, that's the goal. I gave you an algorithm which is to do something, but I am giving can you think of a different algorithm where the edges are coming using this claim? Well, I can construct G prime and use my connectivity solution, right. My problem 1 was checking whether a graph is connected, remember, and so all you do is whenever an edge comes, it will correspond to 2 edges in G prime. So maintain this thing and maintain the spanning forest of G prime, okay, and do the connectivity solution. Okay, people seem to be lost. Good question. What happens to the space? Yes, very good question. So, how many vertices are, if G has n vertices and m edges, how many vertices are there in G prime? 2n vertices and 2m edges, that is all. So, it increases by, just doubles it, asymptotically it is not such a big thing. Okay. So, I mean the reason I want to say is this, checking for bipartition was a little non-trivial, but this theorem tells you, okay, use the connectivity solution and on G prime and check whether G is bipartite or not. Okay. So, this, I mean tomorrow you are going to, or next week you are going to see these reductions, NP complete reductions, something similar where use the solution for one problem to solve some other problem. Okay, that is always useful. Why reinvent the wheel? If you can prove some theorem like this, then use the connectivity solution to do this. Okay, so the third problem I am going to talk about . Given x, y, give me the distance between x and y, right. It is an undirected, unweighted graph. So, distance between x and y is the length of the shortest path between x and y. So, again remember that in the whole theme in this whole thing is that I do not want to remember the whole graph, I want to remember some snapshot, some picture, some fingerprint of the graph, because space is limited, but still I want to be able to answer this question. Okay. And what we said in the case of connectivity or the bipartiteness is that a spanning forest which is really sparse, because each component has only some n minus, or if there are n1 vertices, there are only n1 minus 1 edges. So, in order n log n bits, you can remember enough to be able to correctly answer whether a graph is bipartite or whether it is connected. Okay. But this problem, so again I forgot to say, given your G and x y. Now, think about this problem, even if I store one edge less, because x and y are arbitrary, the query is going to come for arbitrary x and y and ask me whether there is a path between x and y, right. So, even if I do not, if I remove one edge of the original graph and store a smaller subgraph, I may not be able to answer this. So, in particular, you do not know what x and y is, and suppose there is, you have removed an edge of the shortest path between x and y, then maybe the new shortest path will not be exactly the shortest path between x and y. There is a unique shortest path. Okay, so you can show, which you will see when we talk about lower bounds, that pretty much if I have to answer this question exactly, you have to remember the whole graph. So I'm going to now relax and say, okay, I don't want it exactly, give me some approximate distance. Okay. So the goal now is not necessarily to find some d hat xy, which is at most some t times dxy. Okay, t is some parameter. So what I am going to store is a subgraph, because I am limited by space, and because of that I may not be able to answer your shortest path question exactly, but I will store enough so that the shortest path length in this subgraph is not too bad. Okay, it's at most t times. So t is a parameter which we will fine tune as we go along. Okay, so that's the solution we are aiming for. Okay, so let me just say, because computing exact dxy requires, so this is a technical statement, I am not going to prove it, storing the whole graph. So here is the solution. Okay. Again, I am going to store a set of edges. So basically a subgraph of the graph. And starting with empty set. Now when an edge comes, I need to know, should I include it in my graph or not, right? So this, and what is the criteria by which I am going to store? So I am storing a set of edges. So let us say H is that subgraph. H has the entire vertex set and F this subset of edges. So if distance between x and y in H is less than if it's greater than t, then I am going to add it. Otherwise discard it, that is all, right. So I am at any point of time I am storing a subgraph, so the entire vertex set and some subset of edges, let us call them F. Now when a new edge comes, I will check the distance between these 2 points in this subgraph. If it is more than t, then I am going to say this edge is useful, so I am going to add it. Otherwise, I will discard it. Okay, that is my subgraph. That is all. That is my solution, which stores how much. Okay, how much space? We will come to that. So the claim is the distance between x and y in H, I am storing H is at most t times its original distance in graph. Okay, so this subgraph is a good enough approximate approximate, it has enough to find an approximation to the shortest path. Okay. So, this is not very hard to show. Okay, so let us try and prove it. Okay, so suppose x to v1, v2, some vk, y be the shortest path between x and y and g. By the way, this is also called a T-spanner. Okay, you might see this word. So, in the original graph, suppose this is the shortest path between x and y. Will this, will the same path be existing in H? May or may not. If it exists, good, I already have the shortest path in H. Suppose some edge of this is missing in H. Why was it missing? Okay, so suppose some vi plus 1 edge is not in H. Why? Right. So, I have this path v1 or x to v1 to v2, v3 up to vk. This is the shortest path in G, and maybe this some edge is missing in H. Why was this edge missing? There may be path between? No, let us go back to our algorithm. Why did we not include an edge? No, let us just go back. Why did we not include that edge xy? Because the distance, current distance between x and y is less than or equal to t. That is why I did not include. Okay. Later on I added some more edges, the distance might have even become smaller for all you know, but I know that this vi plus 1, this edge may be missing, but there is a path of length at most t in H between these 2 points. So, for every edge which may not be in H, there is a path of length at most t sitting there in H. Okay. So, that is the end of the argument. So, your path of length k may be blown up by at most t times k in H. That is all, because that's the reason we did not include that edge is because there is already a short path. Short means at most length t. Right? If such a path exists. Okay, so I am going to just say hence distance between x and y in H is at most t times distance between x and y in G. So, if you are willing to settle for an approximation factor of t, I do not have to remember G, I can throw away some edges and I store H. But how much saving did I do, right? What is H? Yeah. At this point, the entire argument is whatever at this point. I have an edge coming, and at this point I have to tell what is the shortest path. Right? So, this whole argument is that there is an edge E coming and I do it, and in my current graph, whatever is the current shortest path and what is the shortest path in H. Okay, how much space have I stored? What is the space? Well, I stored this subgraph H, whatever the number of edges in F is a subset of edges I have stored, and whatever that space is. Now, what is cardinality of F? We will resort to another nice theorem in graph theory, which will be again picked up in tutorial. Now, what is the, okay, so before I mention the theorem, let us look at some property of H. What can you say about the length of the shortest cycle in H? This is also called girth. In girth, in H, for example, can I have a cycle of length less than t? Okay, so let us go back again. So, I want to be able to answer the distance queries. So, my idea is that, okay, I mean, I can't answer exactly, give me some parameter, I'll answer up to that approximation ratio t. And what is the algorithm? Whenever there is an edge, if there is already a path of length at most t in the graph between these two endpoints, I discard it, otherwise I add it. That is my algorithm to store what is the subset of edges I add. And I want to argue that the subset of edges I have stored is reasonably small, the number is small. Okay. To argue that, I want to just capture the property of H. What is the property of H? What can you say? Can H have a cycle of length at most t? Why not? Because I asked the way I asked, the answer must be no, right?
Between two vertices, if there is a smallest, we take that, not the other one.
Exactly.
So it is not possible to having cycle between any two.
Of length at most t, right? Because, or even t plus 1. If H has a cycle of length less than or equal to t plus 1, let us look at this cycle, right? And let's look at the last edge added in H in this cycle. So, maybe this was the edge which was added, some E. But notice that there is a path between x and y of length at most t, the remaining edges of the cycle. In that case, I will not have added E. That is my algorithm, right? Because if there is a cycle of, if there is a path between x and y of length at most t, do not add that edge. So, I will not have added that edge. Okay, so that is a contradiction. No, I am going to just say there is a contradiction. So, girth of this graph is strictly more than t plus 1. Now, there is a theorem, interesting theorem in graph theory, which will be left as an exercise. Any graph on n vertices and girth more than t has at most 2 minus 2 by t. Okay, so I am going to something like this, I am not exactly sure. this can be looked at in the tutorial today or on Monday. So it's a pure graph theory question, right? So any graph, all I am saying is its girth is large, then it cannot have too many edges, because this, if you have a cycle, the short cycle, then the cross edges are not present, because that they will give me a shorter cycle. So somehow you can argue that it has at most so many edges. So if I want, for example, a 3 approximation to these distances, t is 3, then this is like n to the 3 halves edges. Okay, so something better than n square. That's all we are saying. Some really subquadratic space is what I'm going to use to store a h. Okay, so in summary, if I want exact distances, I can't do better than just storing the whole graph. I haven't proved it. Maybe it will be proved on Monday. And so I'm going to settle for approximation, and there is a trade-off between the approximation ratio and the space I use. If I really want very good approximation, maybe I'll use more space. If I am willing to settle for a little more approximation, I have low space. Okay, so this is another interesting trade-off between space and approximation. Again, you would have seen it in other contexts in the streaming algorithms. Okay, so last example. Last problem. Maybe find the maximum matching in the graph. Okay, so you all know what a matching in a graph is. It's a collection of disjoint edges. And there are very classical algorithms for finding a maximum matching in any graph. If it's a bipartite graph, you can use the max flow technique to find the maximum matching. If it's a non-bipartite graph, there is a very classical Edmonds algorithm to find the maximum matching in a graph. Okay. So now in the streaming model, what I am asking for is that a new edge comes. What is the maximum matching? What do you store so that you can answer this maximum matching efficiently? Again, it turns out it is one of those where it's very hard to answer exactly without storing the whole graph or something in sublinear space or subquadratic space. So we're going to settle for approximation. So on the other hand, 2 approximation is fairly trivial. Okay, so what is the 2 approximation? Solution: simply maintain a maximal matching. Okay. Do you know the difference between maximal and maximum? In general, it is a generic concept. What is the maximal set and maximum set? Anybody knows? Okay, so maximum refers to the largest cardinality, but maximal says that I can't add any more. Okay, it may or may not be of the maximum size, but it's just that I have a current solution, I cannot add anything more to it. Okay, so let's see an example. So what is the maximum matching in this graph? A, B and C, D, right? So maximum matching is of size but suppose I picked up the edge BC in the matching. Okay, can I add any more? No, and it is a maximal matching. Okay. It is not of the maximum size, but it is maximal because I can't extend it. Okay, that's the difference between maximal and maximum. Okay. Now, anything maximal is in general relatively easy to do because you can just sort of do some greedy approach. I just go and collect something, and I can't, if I can extend it, otherwise you can't, and it's a maximal matching. Okay. So, anything maximal is easy. So, do you see that in the streaming world, if I want to maintain a maximal matching, okay, it's fairly easy, right? I have a maximal, so let's say I maintain a maximal matching, an edge is coming. What action should I do? Okay. Exactly. Otherwise, just add it, right? If that endpoints of the edge, because an edge is coming and the edge may have intersection with the vertex in this graph. If it's completely disjoint from all the edges I have collected, I will add it to my matching. It's another maximal matching. If it intersects one of the vertices in the maximal matching, do not add it. Okay, it's a fairly simple, trivial thing to do when a new edge comes, and I maintain this maximal matching. Okay, so so algorithm, when E arrives, if E can be added to the current maximal matching, add it. Else discard it. Okay, E can be added. What does that mean? That an X and Y are not an endpoint of my current matching. Okay, and this, how much space will it be? Because I am just storing a matching. Okay, if there are n vertices, how many edges can there be in the matching? N by 2 or something. Okay, and each matching has 2 endpoints, each one takes n log n bits, so it's some order n log n bits. Okay, fine. I mean, I really wanted maximum matching and you created a maximal matching. What is the connection? Right? The claim is that maximum matching is at most 2 times maximal matching. So, what I am storing is sort of a too approximate solution, right? The maximum matching is 100, I may be storing some 50, not less than that, 50 or above. Okay, so I am not too far from the optimum. Why is this true? Let's, the very simple proof of it. There are many proofs you can verify this. So, here is my proof. So, there is a notion called vertex cover. How many people have seen this notion of vertex cover? Okay. What is vertex cover? Yeah, go ahead.
So it is a subset of vertices which cover all the vertices of the entire graph.
Cover all the?
Vertices of the entire graph.
Not all the vertices of the graph. All the edges of the graph. It's a set of vertices that cover all edges. So, that means pick any edge, at least one endpoint must be in this subset. That is a vertex cover. Okay. one can show that minimum vertex cover is at most 2 times maximal matching. Why? Because if you take the set of vertices and maximal matching, they will cover all the edges. Is that clear? Right? So, this is my maximal matching. There are a lot of other vertices here, sure. There are more vertices here, lots of edges here and things like that. So, all I am saying is this set of vertices cover all the edges. Why? Cover meaning if you take any edge, at least one endpoint must be incident on this set. Exactly. If there is an edge which is not covered by it, why did you not add it to your maximal matching? It contradicts the fact that this is a maximal matching. Since this is a maximal matching, there is no edge exclusively outside. So, every edge will have some endpoint. So, if you take all this set of vertices that form a vertex cover, so minimum vertex cover size, I mean because this is one vertex cover, 2 times the number of edges in the maximal matching. So, the minimum vertex cover may be even smaller than this. Okay, that's the reason for this, because the set of vertices in a maximal matching, because that's 2 times the number of edges, is a vertex cover. So, the minimum vertex cover may be a different vertex cover, but this is certainly a vertex cover, minimum vertex cover size may be smaller. And this is also not very hard to see that the maximum matching size minimum vertex cover must be at least the size of the maximum matching. These are all some standard graph theoretic things, not very hard to prove. Why is this? Because if you take maximum any matching for that matter, each matching edge requires one vertex to be covered in the in the vertex cover. These are all disjoint. So, one vertex cannot cover multiple edges. So, for each edge in the matching you need at least one vertex. So, minimum vertex cover, any vertex cover should have size at least the size of the maximum matching. So, together you have maximum matching at most 2 times maximal matching. So, in n log n bits in the streaming world, I store only a maximal matching and it is already a 2 approximation for maximum matching. Okay, good. I think I have reached my time. So, that is all I am going to say. Let me summarize what we did. We were looking at streaming model where edges are coming in and we need to answer some query about the current graph, and we care about the space we use. Almost always n square is sort of a lower bound, which we will see next week. But for certain problems, for example, we check connectivity, whether a graph is connected can be checked using n log n bits of space, whether a graph is bipartite can be checked in n log n bits of space. And when it comes to approximation, we can do a t approximation of the distances in some subquadratic space and 2 approximation for maximum matching in subquadratic space. Okay. So, this is the game in graph algorithms and streaming model. Now, we said we are going to do only one pass. Now, you can also ask this question, okay, I do not want to necessarily, moment the edge comes, I do not necessarily need to answer it, I store some information, come back and answer it, okay. Turns out it does not really make too much difference, but that is another set of models in which graph algorithms are studied. And there are very interesting lower bounds which are not very hard to show, to say how much any one pass streaming algorithm must use at least so much space. Okay. So, that kind of reasonably accessible lower bounds which we will see next week by Deepak Rajendra Prasad will give you some lower bound lecture. Okay, we will stop. Thank you.